Hi, this is the third part, Lecture C of Lecture 26 for Differential Equations and Linear Algebra. It's the first time I've done 3 lectures because these different topics fit so nicely together within each lecture. And in Lecture 26C, it's the culmination, our main purpose of applying linear algebra to differential equations. We will see other applications after this, but this is our main thing that I've been emphasizing. I'm going to talk about diagonalization and change of basis as a change of variable, or if you prefer, change of axes or coordinate system to some sort of skew coordinate system as our main application, again, of linear algebra to differential equations. And once again, we will make use of Mathematica a bit like we did in lectures A and B. All right, let's go back to the saddle point example from lecture 24B. This one right here. Let's quickly remind ourselves what the characteristic polynomial would be. Lambda squared minus the trace times lambda plus the determinant. The trace of that matrix is 3. So we get lambda squared minus 3 times lambda. The determinant is 2 minus 12 is negative 10. And that quadratic can be factored as lambda plus 2 times lambda minus 5. The eigenvalues are negative 2 and 5. Positive 5. Double check things. Yes, that looks good. Okay, so these are the 2 eigenvalues. And we can compute the corresponding eigenvectors. Here's what you would get. You would get, with negative 2, you get the eigenvector negative 3, 4. With the other one, with 5, you get the eigenvector 1, 1. This was in lecture 24B as an example there. Then, we could find a general solution. We could solve initial value problems. Or we could talk about this in the context of diagonalization, as we've done when we've been talking about diagonalization. I can take these eigenvectors and make them columns of a change of basis matrix, P. Notice the columns here, negative 3, 4, and 1, 1. Are those eigenvectors. This is the theory about diagonalization. We know that if we do that, then we'll know that P inverse times A times P will be a diagonal matrix D. We know that already. That's the diagonalization theorem. What is P inverse? Use the shortcut formula for the inverse of a 2 by 2 matrix. The determinant of P is negative 7. You've got 1 over negative 7. You swap the numbers in the main diagonal and negate the numbers on the off diagonal. Then multiply the negative 1, 7 through. It simplifies to this. And if D is computed as P inverse times AP, go ahead and check all this. You get this diagonal matrix. That is D. How is this relevant for solving differential equations? One way we saw it was relevant is with regard to the matrix exponential. We saw that our solution function with initial condition y0 of t, we know by the beautiful generalization that I talked about a lot, is e to the ta times y0, where a is this matrix here. But a can be replaced by, if you solve this equation for a, by left multiplication of p and right multiplication of p inverse. A is going to be p d p inverse, where d is that diagonal matrix. And it turned out, using the infinite series definition of the matrix exponential, this is the same as p times the matrix exponential e to the td times p inverse times y0. E to the td, since d is diagonal, is easy to find. Just do this product, you've got your answer. You've got your unique solution, okay, to an arbitrary initial value problem. We're going to do the same kind of thing here. We're going to solve the IVP ultimately, generic IVP, but we're going to do it in what's going to feel like a different way. But they are obviously related to each other. You know, in Calculus 1 and mostly Calculus 2, you use change of variables a lot. Substitutions to help you do integrals, for example. U equals x squared or something might help you do an integral. And you've got to find du to be 2x dx in that case. We can use change of variables here as well. It effectively amounts to changing basis, changing coordinates, if you will. Coordinate vectors, if you prefer thinking of them that way. But I'm not going to in this lecture. I'm going to think more intuitively in terms of variables. Define a new vector variable, boldface capital U, by the following formula. Let the old vector y be p times u, where p is this matrix here. Multiply that, and you might be scratching your head. Wait a minute, didn't I want to define u? Does this define u? Yeah, it does define u as p inverse times y. It's always a little confusing at this point, and some other points are confusing, so you want to pay attention. Once you've got p, you write the old vector in terms of the new vector. Y is the old vector, so to speak. U is the new vector. Using p in this way, y equals p times u. If you want u in terms of y, it's got to be p inverse times y. That can be confusing, so make sure you are careful in thinking about that. I'm going to write these equations down for future reference. It's going to be helpful. So the original differential equation is dy dt equals 2, 3, 4, 1 times y. So there's my matrix A. I'm also going to write down the relationships between x and u, both in this form and in this form. I'll focus on the scalar forms of those. I can write those as systems of equations if I like. X, by this line, is going to be negative 3u plus v. And y is going to be, by this line here, 4u plus v. The other equation defines the inverse transformation, u and v in terms of x and y. U is going to be negative 1/7 x plus 1/7 y, and v is going to be 4/7 x plus 3/7 y. These transformations, linear transformations, really are inverse functions of each other if you think of them as linear transformations, because these matrices are inverse matrices. We already know that, okay? But now I'm writing it in scalar form because that's going to be helpful for us. We might wonder, does u satisfy a differential equation? It is a function of t, if I'm assuming y is a function of t. If I'm assuming y is a function of t, that's going to mean u is a function of t. I can think of it this way. P and P inverse are constant matrices, but y is a function of t. Therefore, u is a function of t. Does it satisfy a differential equation? Well, let's see if we can work it out. Let's think about what the scalar quantities, little u and little v, satisfy. And we're going to see they satisfy a completely decoupled system. Here are the details for finding du dt. This is tricky, okay? You got to be really careful when you do this. What am I using here? I'm starting by using this equation. U equals negative 1/7 x plus 1/7 y. I'm differentiating both sides with respect to t. Du dt is what you get when you differentiate the left side with respect to t. You don't know what u is, but you can still do the abstract calculation. Differentiate the right side with respect to t. Little x and little y depend on t as well. And the derivative is a linear operator, which is the linear transformation on function spaces. But anyway, you'll get negative 1/7 dx dt plus 1/7 dy dt, which is what you see there. Now use the differential equations in scalar form. This up here would say dx dt, look at the top of the matrix, is 2x plus 3y, and dy dt, look at the bottom row, is 4x plus y. Use those equations next. Replace dx dt with 2x plus 3y. Those match. Replace dy dt with 4x plus y. Those match. All right? Simplify, expand, multiply the negative 1/7 through here and the positive 1/7 through here, group together the like terms. For the x term, you get negative 2/7 x plus 4/7 x is positive 2/7 x. For the y term, you get negative 3/7 y plus positive 1/7 y is negative 2/7 y. Now use the fact that x is negative 3u plus v and y is 4u plus v. Substitute those in place of x and y to get this. Simplify again, distribute again. What's the u term? Multiply those, you get negative 6/7 u. Multiply these, you get negative 8/7 u. Negative 6/7 plus negative 8/7 is negative 14/7, negative 2u. And the v's terms cancel. 2v minus 2/7 v minus 2/7 v is 0. The v term goes away. A nice, simple equation for du dt. You can do a similar kind of thing for dv dt. Check all the same things again. In the end, you get the u terms canceling, you get 5v. That's a completely decoupled system. In terms of u and v, the new coordinates. We like completely decoupled systems. We know how to find the answer right away. U would be u0 e to the negative 2t, looking at the top line. And v would be v0 e to the positive 5t. It's a completely decoupled system. In matrix form, the matrix is diagonal. Here are the details to confirm that at the matrix vector level. The derivative of the vector u with respect to t, because u equals the constant matrix P inverse times y, is that constant matrix P inverse times the derivative of the vector y with respect to t. But hey, dy dt equals a times y. Then I can use the associative property and write this way. And wait a minute, if u is P inverse times y, I knew y was also P times u. Y equals pu. Pu. Y gets replaced by pu. And lo and behold, use the associative property again, and I can write it as P inverse times AP times u. But P inverse times AP is the diagonal matrix D, which is this. Wow. Isn't that fun? This is the analogous calculation in one line of vector equations as these two lines of scalar equations. They're both fun in their own ways, I guess. We get a diagonal matrix, a completely decoupled system in terms of the new variable u. The original problem seemed hard to solve, but in terms of this new variable, it's easy to solve. That's the point. That's the application of linear algebra to differential equations. With integrals in calculus, doing the substitution gives you an easier looking integral if you do it right, at least. Same kind of theme. Use the substitution, the new variable, to get a simpler system. That's our main application. Not that we don't have other applications, we do. We've seen them already. But that was the thing that I emphasized at the very beginning of the course as our main application of linear algebra to differential equations. And we won't just talk about it here in lecture 26C. I mean, if it's our main application, we should talk about it some more, at least in lecture 27, with other examples perhaps. I do want to come back to the matrix exponential as well, and come back to difference equations as well, and relate those, and think in terms of determinants of matrix exponentials and how those linear transformations change areas. That's soon to come, and I think it's pretty cool, related to the flow. And the new coordinate system here is new. Change our coordinate system to new skewed coordinates. You might wonder, what do those skewed coordinates look like? What are the axes for this new UV system? Under which the linear system is easy to solve. Okay, now we're going to visualize it. So I'm going to show you the XY phase plane. And you can see what I have in this plane and see it makes sense without thinking about changing coordinates. right? You don't have to think about changing coordinates. Here it is. Added a couple things to this picture that I don't usually have. These orange lines labeled U and V suggestively. Ignore the orange lines for the moment. It is the phase plane. X and Y axes are in black, big black dot at the origin. There's a unique equilibrium point at the origin because the determinant of the coefficient matrix is non-zero. So the only solution of A times Y equals 0 is just the zero vector, just the trivial solution. That's why there's just one unique equilibrium point. The brown line is the x-noc line, solutions cross vertically. The pink line is the y-noc line, solutions cross horizontally. What are these orange lines? Why are they labeled U and V? Hey, those are straight line solutions. Don't they look like they are? Looks like it. Yeah, they are straight line solutions. They're parallel to the eigenvectors. Parallel to 1, 1 in this direction, parallel to, what was it? I think negative 3, 4 in this direction. The eigenvectors for this matrix. Those are straight line solutions, and what this means is the straight line solutions form the new axes for my new coordinate system. That's the connection. The straight line solutions labeled U and V do form my new coordinate system. Remember, in the new coordinate system, the matrix capital D, negative 2, 0, 0, positive 5, the eigenvector for the eigenvalue negative 2 was the negative 4, 3, or negative 3, 4, excuse me. Point negative 3, 4 is right around here. An arrow with components negative 3, 4 would look like that, be parallel to that. The vector field points in the opposite direction, though, because the eigenvalue is negative. Origin is a sink in that direction. And that will be the u-axis, which does correspond to the negative eigenvalue. The other one, the v-axis, parallel to the vector 1, 1, the other eigenvector. Source in that direction corresponds to the positive eigenvalue 5. That would be the v-axis here. In the next picture I'm about to show you, I added in slanted grid lines to make slanted graph paper, skewed graph paper. There we go. This would be the corresponding skewed graph paper in the light orange color that I hope is not too hard to see. You can see these lines here. Hope it's not too hard to see. You can download the PowerPoint if you want to see them better. That would be my slanted graph paper, my skewed graph paper for the new coordinate system UV. In fact, excuse me, this point right there is the point negative 3, 4, because it's going through this first line parallel to the v-axis. The UV coordinates of this point are 1, 0. 1 in the u direction, 0 in the v direction. And this point right here, close to this line, that's the point 1, 1 actually, in the xy coordinates. In uv coordinates, it would be 0, 1. U coordinate 0, v coordinate 1. And that's a closer distance to the origin. That's why these lines are closer together than these lines are. Because that eigenvector that I chose, 1, 1, is closer to the origin, shorter than negative 3, 4. I will show you an animation on Mathematica related to this, but let's do some symbolic calculations first. The change of variables can help us find solution formulas as well. We don't have to use the matrix exponential. We can use the change of variables. In effect, it is using the matrix exponential without saying it is, and we'll see that we get the same answer at the end. So the du dt equation is this. It's completely decoupled, diagonal matrix, easy to solve. I'm calling the solution u equals not phi, but psi. That's psi, spelled P-S-I. It's not the same as phi, but it is a Greek letter still. It's maybe a little dangerous to use such a symbol with engineering majors because that reminds them of quantum mechanics if they know quantum mechanics. And wave functions, this is not a wave function. No quantum mechanics here. Why am I using a psi instead of a phi? Because it's a different formula. I'm also going to use a phi when I use the y-coordinate system. That's my solution function for this differential equation. D is diagonal, it's easy to find. There it is. This is the matrix exponential here. E to the TD is equal to that. What I'd like to do now is I'd like to use this formula to find the solution for y as a function of time. Just use your transformation equations, your substitutions essentially. We know from before y is p times u. But u depends on time, it's psi of t, where u sub 0 is the initial condition in terms of u coordinates. But that's equal to this. There's p, there's e to the td, there's vector u sub 0. This is the product, p times e to the td. And this is the final answer when you multiply it all out. Take time to check those things. That is how y depends on t in u and v coordinates, but I really should figure out how y depends on t in x and y coordinates. So I'm not quite there yet, but we can continue. How? In vector form, we could write the initial condition u0, the initial condition in terms of u and v coordinates. I know that's p inverse times y. Y0. It's p. U is p inverse times y in general. Y is p times u, therefore u is p inverse times y. That works with initial conditions as well. Here's p inverse. There's the initial condition as a vector with x and y coordinates. Do the multiplication, you get this. We're almost done. Finally, to get the solution psi of t, or excuse me, phi of t, phi sub y0 of t, the solution with initial condition y0 as a function of time. I skipped a step here, essentially. That is also equal to e to the ta times y0. But e to the ta is p times e to the td times p inverse. That's p, that's e to the td, that's p inverse. Multiply. This is p times e to the td, which we had up there. There's p inverse. There's vector y0. Multiply these, you get this. I didn't bother multiplying this matrix times this vector. This thing right here, that is e to the ta times y0, which I guess I had at the end, so I didn't really have to write it there. But. And that's a way to get the solution. It's also a way to compute the matrix exponential if you want. That's the last slide. Let's go to Mathematica to finish. So here's our matrix A. Here's the eigensystem. Eigenvalues are 5 and negative 2. 1, 1 goes with the eigenvalue 5. Positive 1, negative 3, 4 goes with the eigenvalue negative 2, the negative 1. Here are my right-hand side functions to help me draw null lines. And this stuff draws the null lines as well as the shading, reminding you that pink means northeast motion, blue means northwest motion, green means southwest motion, and yellow means southeast motion. There we see the null lines plus the straight line solutions. Here I added the grid lines. If you're interested in the code, there was some extra stuff involving flatten and table and infinite line. This stuff in here makes the grid along with graphics. Here's our final thing to note. You can even think about the axes themselves getting transformed under the linear transformation. Y equals P times U, Y equals PU. The x-axis gets transformed to the u-axis. The v-axis gets the y-axis gets transformed to the v-axis. Notice the red line goes from being the x-axis to being the u-axis, and the blue line goes from being the y-axis to the v-axis. What's going on here? How do you describe this geometrically? Is this some sort of weird combined rotation? It's more complicated than the examples we've looked at so far. And in fact, there's a change in orientation, you might say, in that these red and blue lines cross as we transform from one to the other. And the reason for that is because the determinant of the P matrix is negative. What was the P matrix? The P matrix is this thing here. Its determinant is -3, -4 is -7, negative determinant. And it's because that determinant is negative that you get this change in orientation. You get the, as the x gets transformed to u and y gets transformed to v, those lines cross, swapped. In terms of imagining the image of a butterfly, like we did way back when, lecture 5 or so, under this linear transformation defined by the matrix P, the butterfly gets bigger and also kind of flips around at the same time and gets stretched more in this direction than it does in that direction. So it's kind of a complicated geometric effect. It's like a flipping and a stretching in both this direction and this direction, but more in this direction. Corresponding to that eigenvalue 5, was it, or no? I'm forgetting what the eigen. Okay, it's a little tricky to think about. I'm not quite sure yet at the moment how to think about that. Let me say finally something that is another thing that's confusing for people. Thinking about that linear transformation in this P matrix. This is really tricky, but important. Pay attention. We know that a matrix like this is going to map I hat, E1, the vector 1, 0, the unit vector in the positive x direction, to the vector whose xy coordinates would be -3, 4, that I talked about in the picture. It's the column, the first column of P. And the second column tells you what j hat gets mapped to. 1, 1, like that. But here's the confusing part. That equation is y equals p times u. So shouldn't this equation transform u coordinates to y coordinates? And didn't I just say transform x and y to u and v? That's really tricky here. This is all correct. You got to think about it in the right way. Let's think about this picture. When you think about transforming the x-axis, the positive x-axis to the positive u-axis, and 1, 0 getting transformed to -3, 4, what you're really saying when 1, 0 gets transformed to -3, 4 is that this point, right about, where was it? Right about here, It's not letting me draw it. Okay, I'm not sure how to fix it. This point, whose xy coordinates are negative 3, 4, has uv coordinates 1, 0. I already mentioned that 5 minutes ago. uv coordinates 1, 0. If you replace that u with 1, 0, you get y as negative 3, 4. You get its x and y coordinates. Yes, P ultimately transforms the x-axis to the u-axis and the y-axis to the v-axis, but in terms of understanding what it means in terms of these different coordinate systems, if you're looking at, for example, that point right there, its uv coordinates are 1, 0. You replace this with a 1, 0. Its xy coordinates are negative 3, 4. As we know when we think about x and y coordinates, this point has coordinates negative 3, 4. Similar thing happens with the other one. This point close to the origin, xy coordinates 1, 1, has uv coordinates 0, 1. When you plug in 0, 1 here, you get 1, 1. Okay? So it's very tricky. You really have to be careful when you think about it. But I think it's all kind of fun. Thanks for watching.